People who have worked with me on projects know that sooner or later, in most projects, I end up defining a combinator called repeatedly. From one angle, repeatedly is just another form of foldl, but it's just defined slightly differently, and I find that it provides a new perspective that I find quite useful. So in this episode, we're going to talk about this combinator, we're going to define it, and see a bunch of use cases.
Welcome to the Haskell Unfolder, a YouTube series where we discuss all things Haskell. As always, this show is live streamed, so we invite you to submit questions or comments in the chat, and we'll try to show them on screen and discuss them.
Right, so before I show the combinator itself, let me just give a motivational example. Suppose that we have maybe a small game, and we're tracking the position of our character in the game. So maybe we have a definition of a position, and a position could just be an x coordinate and a y coordinate. Maybe the origin sits at 0, 0, as one might expect. And then maybe we have some actions that our character can take, and let's call them steps. And perhaps we can step left, maybe we can step right, maybe we can step up or down, and maybe we can step away. And step away is going to mean however far away you are from the origin, we're just going to move away again that distance.
Okay.
So if we have these actions, then we might define a function that implements a step, right? Executes a step. So we updates our position. So you might imagine that this is not that difficult to define, right? If we're stepping left, well, then x reduces by 1. If we're stepping right, then x increments by 1. If we're stepping up and down, that just changes y, right? And if we're stepping away, then both x and y double. Okay.
Okay. Yeah.
Straightforward enough. So just to have some example to work with, we might step right. So that should give us to position 1, 0. Step right again, 2, 0. Step up, 2, 1. And then step away should be 4, 2. Right? Okay. So what I just did in my head, right, execute a bunch of steps, we might want a function that does precisely that. Right? So we might something called step all that takes a bunch of steps and executes all of them. And I want to define this in terms of step. And this is where repeatedly comes in. I just want to say I want to repeatedly step. Right? So I'm just going to call this repeatedly. And so the question is, what is this function repeatedly? So what repeatedly is going to do is it's going to take a function that updates a b, right? In our case, b is our position.
Pause, yeah.
Pause, yeah, exactly. Given some a, and in our case, that a is step.
Right.
And it's going to give us back a new function that executes this thing for a bunch of a's, right? So we have a list of a's, and we have some initial b. We apply this function for every a that we have, and then we give you back the final b. That's what repeatedly does. If I can spell it, that would help.
So the first argument is step, as we have seen in the example, right? Step all, and then the result is the type of step all, essentially.
Exactly. Yeah, precisely. Yeah. So if I substitute step for a and plus for b, we get precisely what we're interested in here. Okay. So if we have no a's in our list here, if this list is empty, then we're basically done. Right, so we don't need to do anything with this b. And if we do have an a, at least one, then we're going to apply, we're going to apply f, our function, right, to b using this a as argument. That gives us a new b. And now I just need to call repeatedly recursively with the same f and on the remainder of the a's here. So I don't need f in the first case here. And this is the definition. The reason for the bang here, if that's not clear to you, is that suppose that we are repeatedly stepping, then I don't want to build up a large expression that says, when you evaluate this expression, apply this whole bunch of functions to it. So that, because if we did that, then for every call to repeatedly, we would just make this bigger and bigger, right? It would become something like, I don't know, step of step of step of step of origin, right? A big expression like this. And then only when we say, maybe then at the end we print it, only at that point would we actually start evaluating all these step things, right? But as we would do this, that expression would grow very big and we would use a lot of memory. So instead, what we want to do is we want to basically execute that step at every moment. And so that's why this bang is here, to make sure that this is always in long form.
Yeah, I mean, I think the problem here is that repeatedly is just calling itself, but then with a larger argument, right? So if there is demand on the result of repeatedly, if we want to know the result of repeatedly, then like for a while we're traversing the list, we're just getting these chained calls of repeatedly, and the argument is just growing all the time, and nothing is demanding this final argument of repeatedly until we reach the end of the list.
Right.
And that is sort of why we want to force the evaluation of the argument while we're traversing the list.
Right.
And that is like a special scenario here. And I think the same, like, or related reason is that you put the bangs on the post data type, right? On the integer.
Yeah, exactly. Yeah, precisely. I was going to mention that because we now forcing this. I mean, in the case of stepping, right, we're forcing the position. But if the position was itself not strict in its arguments, that would still not do very much. So now, by having the banks on these fields here, it means that when we force the position, we also force the x and the y coordinates.
Yeah.
Okay.
You want to show, like, just so that we can see the example step?
I can do that. So step all example steps, starting at the origin, and we get 4-2 as expected. Okay, that's reassuring. All right. If we look at the type of repeatedly here and we compare it to the type of foldl, we notice something curious, right? Foldl starts with a function from b to a to b, and here we have a function from a to b to b, right? So really what has happened is that just the first two arguments, right, the b and the a, are taken in opposite order. And then we get back, right, if I bracket this like this, a function which itself also, right, takes two arguments in opposite order. Right, so repeatedly looks very similar to foldl prime, and in fact we can define it in terms of foldl prime. So let's try to do that. Let me call this repeatedly 1, just so that we don't have overlapping symbols or repeated symbols. Right, so let me call this repeatedly 2 for now, or repeatedly. So what we have is some f, a bunch of a's, and a b, right? And we want to define this in terms of foldl prime, okay? So that means we need 3 arguments. That third argument, so if we skip the function for a second, then the third argument is the a's that we have. Okay, fine, we can give that. Sorry, that's here.
Yep.
The second argument is the b, okay, we can give that too. Right, so really what we've done is we've just passed these two arguments in opposite order, right, like we said. And now here we need a function that takes a b, right, and an a, and gives us back a b. And we can do that by calling f, passing the arguments in opposite order, right? So this makes it very clear that all we're doing here is shuffling some arguments around. Now, if this thing here, we have an abstraction in Haskell called flip that does precisely this, right? It just takes a function and flips the arguments around. So we can just call this flip f to get the same result. Okay, slightly cleaner already. And now we can do the same thing here. This function here, right, is a function that takes two arguments. Okay, so we can flip its arguments around. So we can define it like this, and then we can flip the arguments. Okay. Now we can eta reduce, right? These arguments are just passed as is on the right-hand side. So we can just delete them, right? We can just remove those points. They're not editing anything useful here.
Mhm.
And now this is flip, apply to foldL prime, apply to flip, apply to F. So I can rewrite this as composition, apply to F. And now finally it becomes very clear that actually we don't need the F either, and we can define repeatedly simply in terms of foldL prime. Now, whether or not you find this easier to read, that's of course, personal preference. What I would say is that this definition makes it very clear that there's very little of interest going on here, right? Really,
that it is really just a rearrangement of.
Yeah, exactly. Yeah, that makes. I mean, I might have to think about this exact definition too if I want to look at the details. But simply glancing at it, it tells me, oh, actually, you know what? Like Andrew said, we just rearrange some arguments.
I actually have some question that I just came up. I mean, just because of your explanation now, and you started with the type of foldL prime. I mean, if you just go by the types, right? The type of foldR also looks very similar, but you decided that you want to make it foldL prime because repeatedly operationally is doing the same as foldL prime and is operationally not doing the same as foldR, right? But I mean, that is some knowledge that you brought to the table, let's say. It's not like just let's look for a function that has a similar type and then see if we can tweak it.
That's fair. That's fair. Yeah.
Right. Yeah.
Yeah, no, that's a fair point. Yeah, I mean, the knowledge that I bring to the table, I guess, is the knowledge that foldL prime uses a strict accumulator, which is something that we do here.
Yeah, I mean, foldL has exactly the same structure of calling itself recursively with an updated accumulator. Right. Just the arguments are in a different order, whereas foldR is really doing something slightly different.
Yeah. I mean, exactly the comparison would, I guess, go beyond the scope of this particular episode. But yeah, you're right. I mean, the type itself is not sufficient to suggest that this should be foldL prime rather than foldR. That's true.
I mean, despite appearances in Haskell, you sometimes have different functions that have the same type or nearly the same type. So just finding a function that has the same type and then pretending it's the same is not always going to work.
Sadly no. That would be nice if that were the case, but okay, so I can make one final generalization of this function, which is because we have a list of A's here, but really we just want anything that we can fold over. Which is in a way anything that can turn into a list. That's another way of thinking about this, and we call that foldable. And so this is the definition of repeatedly that we will actually use. So we just go for anything that's foldable, and then rather than have a list, we have a T array. Okay.
Yeah.
Okay. So.
But in particular lists, right? I mean.
In a particular list, yeah, of course, yeah. So you might ask, okay, why bother, right? What's the big deal? It's just a foldL prime. Okay, we already know that. But I would argue this is a useful combinator, and I want to show this by some examples. So suppose that we have a quick check property that says that if I add 0 to a number, I should get the number back. Right? So this might look something like this. If I add 0 to n, I get n back. Okay. If I check this property, then QuickCheck tells me it passes. Okay, that's good. But it doesn't tell me everything I need to know. In particular, it doesn't really tell me. It says that it passed 100 tests, but it doesn't really tell me anything about the input. And so when you're doing property-based testing like this, where it's generating random inputs, you should always be suspicious of the inputs that you are generating. Are you covering lots of different cases, or are you only covering uninteresting cases? For example, if QuickCheck would call this function 100 times with the value 0, well, then we're not really interested in like 100 different cases. So in order to get more of an insight into that, you can collect some additional information about your test case. There's a function called collect to do precisely that. And so, for example, we can do something like this. If n equals 0, then 0 else not 0. And now if I run my property again, it tells me that the vast majority was not 0 and 2% of the cases were 0.
Can you just show the type of collect quickly so that
for now, I'll just do this. It's slightly more general than this, but
right. So, but basically, you can like pick a label, and then every different label that occurs is going to be listed with a number of test cases that match that label. Right?
Oh, yeah, that's not quite right. Every call to collect results in a table, and that table could have like any number of labels associated with it. So just to
that's what I meant. Perhaps I didn't say it, but that's what I meant. But
all right, okay, yeah. So just to make this clear, like if I have maybe I also test that if n is even, then even, else odd, and now I run it again. I will get two tables, right? One for each call to collect, and it tells me that the vast majority was not 0, and roughly half are even, and roughly half are odd. Okay. So this is very useful, right? If you're doing property-based testing, you should be doing this sort of thing to understand what your property is actually being applied to. Okay, how does it relate to it repeatedly? Well, you could imagine that in more complicated cases, we might have a whole bunch of these collect things. And so we might want to define a generalization of this that just collects a bunch of different statistics, something like this, where we give it a list of these things, right? And then apply all of them. So now we have a list of strings to property to property. And we just want to collect all of them. And of course, the answer to this is, well, we just repeatedly collect.
Yep.
Right? If I try this again, it still works.
That's now putting things into
it's
order. That's
a peculiarity of collect.
Because the dollar was right, is right associative function application. I didn't realize this before. Okay.
Right. So let me show you a slightly more involved example, perhaps. Suppose we want to invert a map. And what I mean by that is, suppose that we have a map that for every A gives us a set of Bs. Oops. And I want as a result a map from every B to a set of A's. Right, so we're inverting it. So what are we going to do? Well, we're going to turn this input map. We're going to take every element of that and insert it into a new map that we're constructing as we go. And so we can do that, right? If we call map.toList, we get a list of pairs, right, from A's to B's. And then each of those, we're going to repeatedly apply some function to each of those things. Starting with an empty map. Now, I should point out...
And here we're using the fact that we have a foldable version of repeatedly, right? Because... Or are we not?
No, because this gives us a list.
Because this gives us a... Yeah, right. No, but...
The foldable instance would just give us the elements, and I want both the keys and the elements.
So. Right. Yeah, no, sorry. Okay.
So just as if you're new to, relatively new to Haskell programming, one useful workflow that I find very useful is if I have some function like this, I can give it a name. And because the Haskell server that sits underneath this knows what the type of this function needs to be for this to be type correct, I can then just ask, well, just define this thing. Give me a definition of the right type with a hole. I use this all the time. I find this very useful. Right. So, okay. So this is what we want, right? We have an element of the original map, and we're updating our resulting map for this particular element. Now, I want the A and the set of B as two separate arguments. At the moment, it's a pair, but we don't, that's not very currying friendly. So I want to define it like this, in which case we have a combinator in Haskell that takes a curried function like this and turns it into an uncurried function that takes a pair, and it's called uncurried. Okay. All right. So we have an A, and now we want to update this map here for every element in this set. For every B that we have, we want to update the map at that B and insert this particular A. Right, so we want to repeatedly, repeating over this set, and now we are really taking advantage of the foldable instance, repeatedly insert for that B this particular A. Right? So repeatedly insert A. And now again, I do the same trick, right? We have some undefined function. I ask, please give it to me. Okay. So now we have an A and a B, and we want to insert that A for this particular B. And so we can do that by, there's an operation on maps called alter, which can either update an existing element if it's already in a map, or insert it if it doesn't exist yet. It takes two things. It takes a function that actually
can
does
also
the
actually
updating.
delete it, right? I mean,
it can even delete. Yes, that's right.
Yeah.
And then the key where we want to apply this function. So the key is B here, right? And what we want to do is we want to update the set, right? So let's call that update set with A, right? A is the argument. We want to insert A into the set. So the same trick one more time. Okay, so yeah, like Andrea said, it can delete it. So it takes a maybe as an argument. So this is nothing if the map is not, if the element is not already there in the map. And it also returns a maybe. And if you return nothing here, it will delete the element from the map. We never want to do that in our case, but it's a very general type. So we have an A, and then if we don't have an element in the map yet, we just make a new one, right? Which is a singleton one containing just A. If it does already exist, then we just want to insert A into that set. And that's the definition. So yeah, I think this is
very nice.
Quite clean. Okay. Finally, let's think about the monadic case. So suppose that our step function could fail, right? So maybe stepping left, right, up, or down always succeeds. But if we want to step away, right? Well, remember stepping away was look at where we are in relation to the origin, and then just double that distance. Perhaps we are saying, well, actually, if you are at the origin, we don't yet know which direction to step away in, and so we're failing. We can't do that. So in that case, step is going to have a monadic type, right? In this case, the monad that we are choosing is either string, right? Either an error message or an updated position. And then for all the cases that always succeed, we just return right. I could also have said return here or pure. It's all the same. And then for step away, we can still do the stepping away, but now we can check if we are actually at the origin, and if so, give an error message. So if we are at 0, 0, then we give an error message here. And so for an example that would fail is if we are stepping right and then step left, we are back at the origin, right? This is 1, 0, back to 0, 0, and now stepping away, this would fail. Whereas in the original set of examples, we had right, right, step up, at which point we were at 2, 1, and then stepping away would for 2, right? So this one should succeed. But what I just did in my head was repeated application of step, but now with this monad there, right? So we need a version of repeatedly that allows for a monad to be present. So if we start with the definition of repeatedly as we had it initially, right? Actually, let me just start with the one that we explicitly wrote out, like this.
Yeah.
And I call this repeatedly m. Then our function here, that's our step function, remember, is now going to have some monad, and we don't really care what that monad is, but any monad m. And then the whole function also becomes monadic. So we have, like, the structure follows very, very closely the structure of the original function. If we have no a's left, then we just need to return the b, right? And in this case, we really need to return the b. Here we could just give the b directly, but now we need to return it in some monad m, right? So we need to say return b, or if you prefer pure b, that would also be the same. I prefer, that's a matter of preference, I suppose. Whereas if I do have at least some a, then we need to update we need to apply f to our b with this a as argument, right? But that is now a monadic action, so we need to use do notation or bind to do this. So we apply f to a and b, we get a new b out of it, and now we can call ourselves repeatedly with the remaining of the a's.
Yeah.
So if I just try this repeatedly m1 of step m, starting at the origin.
You need the example steps.
Oh yeah, sorry.
So that was the original example steps. So that is succeeding, right?
Right, exactly.
So it's not hitting the error case.
Yeah.
And
So
now
the right
example steps 2 should be failing.
Yeah. Okay. Now, of course, for repeatedly, we said actually this is just foldl. So the question is that also true for the monadic version? And the answer is yes, with an asterisk, slightly of an annoying asterisk. But so if I just call this repeatedly m, before, just to remind ourselves, actually, let me use the version without foldable generalization. We don't really need it. Just to keep things a little bit simpler. Right, we just said it's flip after foldl prime after flip. And if we look for a monadic version of foldl prime, we won't find it in the base libraries. That doesn't mean that we can't define it if we wanted to, but it's not there. There is a version of foldl, and it's called foldM. So this one works, but it's not quite as strict as one might like. It's as if we didn't have the bangs here. Right, so this is not quite the same function. One could argue that it's okay because depending on the choice of m, we can recover that behavior. But I personally find this somewhat unsatisfactory. So I would have preferred that there's a foldM prime in base, but it's not there. So actually, in real code, when I define repeatedly m, I define my own foldM prime and then define exactly this. But yeah, that's I guess not critical here. Okay, that's all I had to say, unless there are any questions.
No, at least, I mean, unless someone wants to ask a question right now. I had already been asking a couple of minutes ago.
Okay.
I think it's all clear to me. Oh, no, actually, we do. Yeah, I mean, but it's basically just a reiteration of what you just said. So I'll bring that up. Louis, is there any reason to not have foldM prime?
I mean, Anders and I were discussing this prior to the episode, and my feeling is that it should be there. It's strange that it's not there.
I think it would be nicer because it's kind of like, I mean, already foldl prime has for a long time like given its importance, right? I mean, so it's really important if you do this accumulator thing on a list, like a left fold, that you make the accumulator strict in a lazy language like Haskell. And foldl without the prime should basically never be used. I mean, there is like you have to really try very hard to find examples where foldl makes sense and foldl prime doesn't. So foldl prime should be in the prelude, and actually, like, that's also something that we just discussed before the episode. That I think it will now, after years and years, will finally be in the prelude in GHC 9.10 in the upcoming GHC release. And so in that sense, but you can see that in the libraries, even foldl prime has for a long time been sort of considered less important. I think the argument with foldM is that, as Etzko has hinted at, is that like if your monad is sufficiently strict, and like in the definition of bind, and in practice, many monads that are being used in practice, like IO or maybe, or also either, are like in their normal definition sufficiently strict, then you don't really get the same problem. But you may want to use foldM on monads which are not strict. Like, I mean, one case is, for example, you might want to instantiate it to the normal plain identity monad, and you might expect that you get the original repeatedly back, and you don't,
Right.
because like with the identity monad, you are then losing the strictness. So yeah, so you can argue foldM does not exhibit the problem to quite the same extent as foldl, and you can often work around it. But as Etzko said, I think I also agree. It would just be nicer. It would be more symmetric. It would be less of a surprise if foldM prime would exist as well.
Yeah.
Okay, I guess.
All right.
Yeah.
All right, then I guess we should leave it there.
Yeah. All right. So thank you for watching this episode of the Haskell Unfolder. If you enjoyed it, please like and subscribe, and feel free to leave comments in, like, if you have further questions, to leave comments in below the video. We are now going to leave the chat open for a couple more minutes in case there are any late live questions, so that we can address them immediately. Otherwise, see you again. We don't know exactly yet when the next episode will be, but it will be soon. Right. Yeah. Thank you.